First of all, let me thank the organizers. In fact, nobody is here. But anyway, it's a very, very difficult job to organize such kind of conference, and especially Professor Abdullah, who came here from Turkey several days before the conference and organized a lot of things. And I saw this, and I very appreciate this such kind of efforts. Okay, I will talk about fixed point semigroups, and actually this some kind of complex dynamical systems. But the history of complex dynamical system so long, and that cannot be given in a 1 hour talk. Therefore, I would like to make a short review about this subject, and to talk about some historical results, some classical results, and somehow to connect them to the modern applications and modern development in this subject. If we talk about complex dynamical system, we always should mention these 4 people who was the roots of this subject. Is Karl Schwarz, Gaston Julian, Julius Wolff, and of course Konstantin Karatadori, who worked on geometric function theory and complex dynamical system, and they were founders of complex dynamics. First of all, if we talk about holomorphic mappings, I would like to define this notion because we will talk not only one-dimensional situation, also higher dimensional situation, even complex Banach space, and just a mapping F from D to X on domain D is said to be holomorphic if it Fréchet differentiable at each point of Z. This is one can define by using power series, Taylor series, or whatever, and there are different definitions, but all of them are equivalent to this one, and the simplest one in the complex sense differentiability means holomorphic. Of course, if we look at a set of holomorphic mappings which are mapping a domain D into itself, we will have a semigroup with respect to composition operation, and we will use this notation whole D just instead of whole dx. Just a small remark that in every Banach space, especially in one-dimensional case, of course, each self-mapping of holomorphic mappings is Ronen expansive with respect to a metric rho, which is called the hyperbolic metric, a hyperbolic metric which can be introduced for each bounded domain, even in Banach space, and in particular, if you have, for example, the open unit, you can define such metric by using Poincaré formula, arctangent hyperbole of the Möbius transformation. What does it mean? Möbius just this transform of the unit disk into itself, and each holomorphic mapping satisfies this inequality with respect to this metric, so it's Ronen expansive. Why it's important? Because one can use for the study of fixed point theory one can use this inequality in non-expensive mapping with respect to the metric, so-called metric fixed point theory. And then we can combine metric fixed point theory together with holomorphy, and this mix makes the subject very attractive and very well developed. Okay, what are general problems which we study usually in fixed point theory? Of course, the existence of the fixed point, uniqueness, or structure of the fixed point set if you have more than one fixed point, and iteration theory in the sense of asymptotic behavior, embedding problem, backward iteration, rigidity, interpolation problem, and so on, so on. For the one-dimensional case, the classical Don Joa-Wolff theorem tells us that if you have a holomorphic self-mapping of the unit disk, then if F is not identity and is not an elliptic automorphism, what does it mean, elliptic automorphism? Just a rotation around fixed point. For each other situation, you will have that there is exactly one fixed point such that, even in delta bar, such that all iterations converge uniformly on compact subset to this point. This is classical and well-known Don Joa-Wolff theorem, which is today is one of the most important tools for the development of complex dynamics for the one-dimensional case as well as for higher dimensional case. It's funny that this theorem was obtained simultaneously by Don Joa and Wolff, but it was published in the same volume of Contra 2, and each paper, the paper of Don Joa was published in previous paper to Wolff. So, but obviously there were no internet at that time, and therefore they could not know about this result. But the problem or conjecture about this was stated about 50 years before. In probability theory and branching processes and population growth, this conjecture was stated by many people, but was proved only in 1926 by Don Joa and Wolff independently. Okay. Just some very simple examples. This is the first case is a rotation, therefore there is no convergence, but this is a unique situation when you have no convergence. Otherwise, the sequence of iteration should go to the fixed point. It can be fixed point inside or maybe on the boundary. And in this situation, when the iteration converges to the boundary, like in this very simple affine mapping, you will have that F has no fixed point inside. A little bit more complicated situation if you have such kind of fraction linear transformation. You have two fixed points, but only one of them is attractive in point. The other one is repelling. And interesting situation, an interesting case for complex dynamics is the following example, which show us that we have also two fixed points. One of them is the origin, and the second one is 1. This one is the Don Joa-Wolff point. In other words, this is an attractive fixed point, and the second one is a repelling fixed point. But if you look at this picture, you see that there is also the convergence to this point when the time goes not to infinity, when the time goes to minus infinity. And therefore, but you see that for some points the trajectory goes outside the unit disk, and for some point inside the unit disk. So what is the problem? What is the question here? The question is what the whole collection of such point such that the trajectory goes to this point 1 when t goes to minus infinity. And for this special example, this collection is just also the disk, but the disk is properly inside the open unit disk, which is our model, and this domain is called backward flow invariant domain. And the problem is how to find this backward flow invariant domain, especially maximal, because you see that there is also backward flow invariant domain here, and this circle is also a backward invariant domain, but this one is maximal. If you take a point outside this domain, the trajectory will go outside the whole disk. And in addition, it turns out that this semigroup becomes to be a group of automorphism of this subdomain. This is not the group of automorphism of the whole domain, but this is the group of automorphism in this subdomain. And therefore, this question can be rephrased as find the subdomain such that given semigroup becomes to be a group. And it turns out that this is exactly happens when this semigroup has an additional fixed point in the sense that there is not only attractive fixed point, there is also a repelling fixed point, and this repelling fixed point must be always on the boundary, not necessary, not inside, only on the boundary. I will talk about this phenomenon a little bit later, but I would like to go back to classical Schwarz lemma and to show you what is a modern problem in this very, very well-known lemma. The classical Schwarz lemma just says that if you have that 0 is the origin is the fixed point, then you have that each disk with smaller radius is invariant under this matrix. But here we have the following phenomena, that a modulus of f prime of 0 is less or 0 or equal to 1. And if f prime of 0 is 1, there is only unique mapping, which is called rigidity mapping. So in this situation, there's just identity. There's just the identity mapping. Only one point, information on one point, you know what you know. You know that f of 0 is 0, f prime of 0 is 1. Gives you by the Schwarz lemma, gives you information that this is only one mapping. The same problem was conjectured by Alfors, that the same holds when not 0 is a fixed point, when fixed point is on the boundary. But this conjecture is not true. I will say about this phenomenon a little bit later. Okay. Returning to Schwarz lemma or Schwarz-Pick lemma, in general, they just written in raw metric, in a hyperbolic metric. The Schwarz-Pick lemma, we can say the following: that f, it belongs to a whole of delta, is holomorphic self-mapping, in other words, and tau is a fixed point. Then the equality f prime of tau, same demand. F prime of tau is equal to 1 gives you that F is an identity mapping. Only recently, Filippo Bracci, Roberto Taurasi, and Fabio Vlacci have proved the following result, which of course is the generalization of the Schwarz lemma in this sense, in the second part of the Schwarz lemma, rigidity properties, that if you have two commuting mapping and they have the same derivative at the fixed point, then they must coincide. And it's, of course, if you take one of them just identity, you will have Schwarz lemma because every mapping commutes with identity. So this, but you look at the difference between this result. The first result of Schwarz was proven in 1869, and this only in 2002. Because techniques completely different. Okay. Another, if I will show you just the picture. A boundary analog of the Schwarz lemma is the so-called Julia-Wolff-Caratadori theorem, which states that if you have no fixed point inside, then you must have a fixed point on the boundary, this point tau, such that each horocycle internally tangent to this point should be invariant for this mapping. So if you take just a point z here, you will have that f of z must lie inside this horocycle. So this is not concentric horocycle like for 0, but they must be tangent to the same point at the boundary. Okay. So we have, for the one-dimensional case, by using the classical result, we have the so-called grand fixed point theory, which combine Don Joao-Wolff theory and Julia-Wolff-Caratadori theory. This theorem says that if F has no interior fixed point, then there is a unique attractive fixed point on the boundary, and for this point the characterization is that the derivative is a real number. And not only a real number, this number is always bigger than 0 and less or equal to 1. If it's less than 1, the mapping is called hyperbolic. If it's bigger than 1, is equal to 1, the mapping is called parabolic. But there is no situation when alpha is bigger than 1. So attractive fixed point cannot not have the derivative of this point, which defined by this interior approach, non-tangential approach, and should be a real number and less or equal to 1. A lot of papers over 70 years after the work of Don Joao-Wolff deal with different generalization of this theorem, but it's a very long story. Okay. If we jump to infinite dimensional case, because the difference between higher dimensional case and one-dimensional case is just infinite dimensional or one-dimensional case, because for finite dimensional case you can use different compact arguments to get the same result, but the problem is very essential problem is for infinite dimensional case, because the ball is not compact in the general Banach or Hilbert spaces. Okay, and the problem is that in general Banach space you not always can get the existence of fixed point. Take just this very simple mapping in the Banach space C0, and this mapping has no fixed point in X. Why? Because if it has fixed point, it should be half, 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 half in each place. But half, half, half doesn't belong to C0. Therefore, this simplest example which shows that not necessarily even holomorphic mapping. In our example, this is just a fine mapping, so holomorphic, not necessarily has a fixed point. So the problem in general is about existence. In 1917, Earl and Hamilton established this result, which very powerful tool for the existence of fixed point, and they prove that if the image of H lies strictly inside the domain, then it must have fixed point, and this fixed point unique, and moreover, this point is attractive. How they prove this result? Attractive in the sense that all iterations uniformly converge to this point. How they prove this result? They just show that the geometric condition is equivalent to that fact that there is a metric, this Carateri metric, such that the mapping becomes to be strict contraction with respect to this metric. After that, you can use, of course, Banach principle to get the existence and the uniqueness and convergence, whatever. But the main point, a crucial point in this theorem is that to show this inequality, this was difficult. Okay? A little bit more general assertion, but for a reflexive Banach space, was proved by Victor Hatzkevich, Shimon Reich, and myself, which says the following, that in Earl Hamilton theorem you have that to require that the image lies strictly inside the domain. In this theorem, it's enough to require that image for the boundary f of x is far away from x. And then you will have that there is only one fixed point, and the same conclusion like in the Earl Hamilton theory. So the very famous problem for Banach spaces to find all Banach spaces such that even for ball we have the fixed point theory. Like in C0 we have no fixed point. But my conjecture is that if you have a reflexive Banach space, then each holomorphic mapping of the ball has a fixed point. There is no counterexample till now, but there is no proof of this conjecture, unfortunately. But this is a conjecture that what is specific for C0 is not reflexive Banach space. And therefore, one can, this conjecture was proved for several Banach spaces. For Hilbert space, for example, by Gebel-Stachura and Gebel-Reich and Tadeusz Kuchumov and Itai Shafrir, and even for multiplication of Hilbert spaces, but there is no proof for general reflexive Banach space. So this open problem. Another problem, if you have that fixed point is not unique, the question is how many fixed points there are inside. For the Hilbert space, the answer was given by Walter Rudin, and he just proved that fixed point set is just an affine manifold in the Hilbert ball. Therefore, either you have only one fixed point, or you have the whole submanifold of the point. In particular, if 0 is a fixed point, like in this picture you see, then this is just linear submanifold because it passes through 0, you find submanifold. And therefore, you have like in Fredholm alternative. Other, but this is not Fredholm mapping. Pay attention about this. Just a general holomorphic mapping is not necessarily Fredholm, but you have the following phenomena. Either one fixed point or linear submanifold. And this was for the first time very strange because the mapping is not linear. This non-linear mapping, and you can find a lot of examples of non-linear mappings in the Gilbert ball given by integral equation, and just you take some power series representation, but the fixed point set is linear. Moreover, Rudin proved that actually this fixed point set is a fixed point set of linear operator given in one point. You take just the Frechet derivative at the point 0, and you have the fixed point of the Frechet derivative the same of the whole domain. And therefore, you have again an extension of Schwarz's lemma for the Hilbert ball. Why? Because if you have that A is identity, therefore fixed point set is the whole ball, and this means that this mapping is itself identity, nothing else. Okay, because fixed point set is the whole ball space. For general Banach space, the fixed point set is not necessarily so nice. You have different structure, but it can be shown that even for general Banach space, the fixed point set is a holomorphic retract. I want to go inside this subject, what does it mean, retract, retraction, and whatever, but in simple words, what does it mean, retract? This is just very, very smooth and regular, very smooth and regular submanifold. So this is like in the linear case, but it can be just changed by very smooth, complex analytic submanifold. So this is not necessarily fine or linear, but it's always the fixed point set, always is a submanifold, like in this. It was simultaneously proved by Jean-Pierre Piguet and myself. Obviously, this time also the internet didn't work yet, and we didn't know about the same result obtained by Jean-Pierre and myself. Later on, we met each other and discussed this theory. Okay, and it turns out that actually you can, once again, to describe in the spirit of Schwarz's lemma, but in general Banach space, by using the spectrum of linear operator, you can describe when this fixed point is 1 or this is the whole submanifold. It turns out that it just depends on the spectrum of linear operator, which is given by the Frechet derivative at the fixed point. Okay, at the fixed point. In particular, if spectrum lies strictly inside the unit ball, unit disk, then tau is a unique attractive fixed point. This is equivalent. So by using not Frechet derivative, its spectrum for linear operator, you can describe all situations. So if you find only one fixed point, you can for example, even for finite dimensional case, you can calculate the Jacobi matrix and the spectrum, the eigenvalues of the spectrum, and if all eigenvalues are inside the unit disk, you will have that the point is only 1, the fixed point only 1. If you have that fixed point is on the boundary, and it is also 1, exactly 1, then you will have the whole manifold. Infinitely many fixed points inside the ball. Okay? And then just picture for what I said before. What is the location of the spectrum? Okay, this literature, my beloved book of Schoenstein, the Schwarz lemma, which you can find everything from the Schwarz result for this year, 1989. Also, for one-dimensional case in my book, Semi-Groups into Geometric Function Series, this book of Shimon Reich and myself, and I would like to pass to go on by the rigidity property. Once again, I return to the problem. What is the problem? Whether these conditions are enough to be sure that the mapping is identity. Is what shown by, it was shown by Kranz, Jones and Kranz, that this is not enough. You have to put for the boundary point 2 additional conditions. That's the second derivative and the third derivative, and then the conclusion is right. That for this situation you have an analog boundary, analog of the classical Schwarz lemma, but you have to add 2 additional conditions. As the second and the third derivative are 0. This theory of Jones and Kranz, which was formulated in such a way, and I should tell you that this result of 1994, even in my home collection, I have more than 200 papers about this result. 200 papers since 1994. It is amazing. For 20 years, 200 papers only on this result. Discussion and different generalization only on this result. So it's a very powerful tool for complex dynamics. Because I have no so much time, I would like shortly to tell you about continuous semigroup. Continuous semigroup, this is like iteration, but it can be given by just such kind of differential equation. The very interesting phenomenon which was first proved by Bergson and Porter, that each continuous semigroup is differentiable with respect to parameter. This phenomenon does not hold for general nonlinear operator, but it holds for nonlinear holomorphic operator. It was surprised by and was proved first in one-dimensional case by Bergson and Porter, and then by Markov-Vater, and for general Banach space for higher dimension case, but finite dimensional situation, and for general Banach space it was proved twice by Shimon Reich and myself, because in the second paper we talked about not only holomorphic mapping, we're talking about non-expensive, for a semigroup of non-expensive with respect to hyperbolic mapping, and it turns out that the same phenomena holds. And therefore, you can study what's about fixed point, common fixed point for the semigroup. And it turns out that you have the same phenomenon like for discrete time semigroup or iterations. And this phenomenon is that if you have no fixed point and fixed point inside, you have common fixed point on the boundary, which can be characterized by this inequality, and this inequality gives you in hyperbolic metric actually the rate of convergence, which is the exponential one. And what is beta here? Beta here is just a derivative, which in fact also is a real number, is derivative of the generator at this point. Okay? And therefore, you can also formulate the same rigidity problem for generators. Because if you have the generator is 0, this is the same if you say that the semigroup, each element of semigroup is just identity. So you would like to recognize what is the situation when generator of a semigroup is 0. And this situation is enough, once again, to tell that if you have 3 derivatives which are 0, then you have that. And the last slide I would like to show you, I will jump a little bit ahead, about flow invariance conditions. About flow invariance condition, and to show you this picture. Okay? This picture was given by Mark Yellen, he is here, Larry Zaltzman, and me, for to show how many backward flow invariant conditions can be for holomorphic mapping. If you have that the generator has only one null point on the boundary, then you have only one backward flow invariant domain. If you have 2 null points, like in this example when n is equal to 2, you will have 2 flow invariant domains. And this computer picture is exact, and you see here how what is the behavior of the semigroup. What does it mean backward flow invariant domain? Once again, it means that for this subdomain, the semigroup becomes to be a group. So for this point, for each point inside this domain, the trajectory is well defined for each real t, not only for positive t. The solution of differential equation, the differential equation is solved for each t from minus infinity to plus infinity. I think that at this point I will stop. And thanks for your attention.
Any questions? Is there anything known for locally convex spaces in this framework?
Some results there are for locally for Shoikhet spaces.
Yes.
Yes, but a little is known, unfortunately. Because it's very good to know for locally convex domain because the semi-group structure is very well developed by Yoshida, whatever. But for non-linear situation, we have a lot of results about this, but some results there are. Okay, but it's very good equation and a very good problem to study and to develop this theory for locally convex domain because you will have a lot of applications.
Thank you very much for a very nice lecture.
Thank you.
Any other questions? Right, thank you. The next speaker here.